Section: Introduction. In this section, we discuss the remarkable impact of large language models, LLMs, on the field of machine learning. We have observed a shift from training neural networks from scratch on specific datasets to utilizing pre-trained LLMs and crafting effective prompts containing relevant examples and instructions. This change has led to an interesting comparison in problem-solving approaches. Traditionally, neural networks were optimized in a continuous numerical space using gradient descent, whereas with the new approach, we optimize the input prompt of an LLM in a discrete natural language space. This raises the question of whether a pre-trained LLM can function as a model parameterized by its natural language prompt. To address this question, we introduce the concept of verbalized machine learning, VML, where natural language serves as the representation of the model parameter space. The key idea behind VML is that we can define a machine learning model using natural language, and the training process involves iteratively updating the natural language representation. This framework opens up new possibilities for interpretability, as the knowledge learned from data is stored and summarized in natural language. Specifically, we consider the input text prompt of LLMs as the model parameters being learned. However, optimizing over a natural language parameter space presents challenges. Inspired by previous work that views the optimizer as a function parameterized by a neural network, we parameterize the optimizer function as another LLM. This optimizer LLM generates the next step model parameters based on the current model parameters, training data, and loss function. In VML, the optimizer LLM iteratively updates the learner LLM to achieve the training objective. Compared to traditional numerical machine learning, VML offers several advantages. Firstly, VML provides a straightforward way to incorporate inductive bias into the model using human-interpretable natural language. This linguistic parameterization enhances interpretability and adjustability of machine learning models. Secondly, VML automates model selection during training based on the data and prior knowledge expressed in natural language. Thirdly, each model update in VML is fully interpretable, as the optimizer LLM can explain the reasoning behind the update. An important aspect of VML is its unified representation of data and model at the token level using natural language. Unlike numerical machine learning, VML treats both data and model as part of the text prompt, similar to the concept of stored program computers. This connection underscores the significance of text prompts in VML, which act like computer programs and enable LLMs to solve problems without prior training. Our contributions include formulating the VML framework, demonstrating its effectiveness in solving classical machine learning problems, designing a concrete VML algorithm with a text prompt template, and conducting empirical studies on injecting verbalized inductive bias. We also evaluate the performance of VML components to gain a better understanding of its capabilities. Section Summary. In this section, we introduce the concept of verbalized machine learning, VML, where pre-trained language models are treated as function approximators parameterized by their text prompts. VML leverages natural language to define machine learning models and train them iteratively through language updates, offering interpretability and automatic model selection during learning. By using natural language prompts to parameterize functions, VML provides a unified way to inject inductive bias and solve classical machine learning problems in a data-driven manner. Section: Verbalized Machine Learning. In this section, we delve into the concept of verbalized machine learning, VML. We transition from traditional numerical machine learning to VML, where we represent both the data and the model using natural language. Instead of storing models as incomprehensible numbers, we view a language model, LLM, as a function approximator defined by its text prompt, leading to the VML framework. This framework offers strong interpretability and makes it easy to pinpoint the cause of model failures. In VML, we parameterize machine learning models with natural language, constraining the model parameters to be text token sequences from a set of human-understandable language sequences. The natural language space in VML is discrete, sequential, and human-interpretable, allowing us to easily incorporate prior knowledge and desired biases into model training. Empirical evidence shows that the model parameters often describe the underlying patterns discovered from the data in a language format. The core idea of VML is to use a language model as a function approximator, where both the input data and function parameters are represented with text tokens. By freezing a pre-trained language model, we can treat it as a deterministic or probabilistic function based on the temperature parameter setting. We illustrate how a classical machine learning problem, such as least square regression, can be formulated in the VML framework. Optimizing the model parameters in VML involves prompt optimization, where we update the model's language characterization to incorporate new information and modify existing knowledge. We approximate the next step model parameters using another pre-trained language model acting as an optimizer, which helps in efficient training and model improvement. The optimizer in VML offers advantages such as automatic model selection, detailed explanations for updates, and direct user interaction, enhancing the understanding and performance of the VML framework. Section Summary. In this section, we explore the concept of verbalized machine learning, VML, which involves using natural language as the parameter space for machine learning models. By representing both data and model parameters in a unified token-based format, VML enhances interpretability and allows for easy tracing of model failures. The core idea behind VML is to utilize language models as function approximators, where the model is parameterized by a natural language prompt, enabling easy incorporation of prior knowledge and inductive bias into model training. Section: Discussions and Insights. In this section, we discuss and provide insights on variable machine learning, VML, as a unified framework for incorporating inductive bias. Over the years, there has been a quest for a unified framework to capture various inductive biases. Different types of data require different models to encode these biases, such as graphical models for random variables, recurrent networks for sequences, graph networks for graphs, and convolution networks for images. VML offers a unified approach by using natural language to input inductive biases, making it highly adaptable for encoding complex biases. To include an inductive bias regarding the hypothesis class or prior knowledge about the problem, we can simply combine a system prompt, theta_text prior, a fixed text describing the bias, with the model parameters, theta. This results in the final model parameters being theta_text prior, theta, where only theta is trainable, and theta_text prior is provided by users. Comparing VML with prompt optimization, both aim to generate a text prompt automatically for a specific target. However, VML differs significantly as it aims to discover a verbalized data pattern that serves as the model parameters for the learner, while prompt optimization focuses on creating a generic instruction without altering the original meaning to enhance question answering performance. We will qualitatively compare the learned prompts of both approaches in the experiment section. VML allows for interpretable knowledge discovery since the model parameters, theta, are in natural language, making it easier to comprehend the underlying patterns and decision rules used by the model for predictions. This interpretability enables VML to uncover new knowledge that humans can also benefit from. In conventional machine learning, model parameters and data are typically treated differently, akin to the Harvard architecture that separates instructions and data storage. In contrast, VML stores both data and model parameters in the text prompt as tokens, resembling the von Neumann architecture that stores instructions and data in the same memory. This distinction makes VML an intriguing avenue for exploration. We showcase the capabilities of VML by revisiting basic machine learning tasks like regressions and classifications. These tasks involve finding the optimal theta that best describes the mapping from input data to output. Our experiments demonstrate how VML effectively solves these tasks and determines theta. For our experiments, we utilize the instruction-tuned Llama 370B for the language model, LLM, unless stated otherwise. Each task's training set comprises 100 data points, with a batch size of 10 for optimization steps. We evaluate regression performance based on training loss, model predictions in interpolation and extrapolation settings, and classification accuracy on test sets. During optimization, we incorporate momentum-inspired techniques to stabilize training. The results of our experiments are presented through training loss computation, visualization of the learned model, and tracking model parameters at each training step. The LLM computations are performed on a node with 8 A100 GPUs, with multiple queries made for model evaluation and optimization at each training step. Overall, regression tasks take approximately 10 minutes per epoch, while classification tasks require around 16 minutes per epoch, with an additional 6-minute overhead for evaluating the decision boundary grid. Section Summary. In this section, we discuss the concept of VML as a unified framework for encoding inductive bias, which has been a long-standing pursuit in machine learning. VML utilizes a natural language portal to incorporate inductive biases, allowing for flexible encoding of complex biases by concatenating a system prompt with model parameters. Additionally, VML distinguishes itself from prompt optimization by aiming to discover verbalized data patterns that act as model parameters, enabling interpretable knowledge discovery and resembling the von Neumann architecture in machine learning. Section: Linear Regression. In this section, we generated training data from linear, polynomial, and sinusoidal functions with added Gaussian noise. For the linear function, y equals 3x plus 4 plus epsilon, where epsilon follows a Gaussian distribution and x is uniformly distributed between 0 and 2. Initially, our model parameter, theta_0, was set for a regression task from real numbers to real numbers. Through training, we observed the model improving and converging towards the ground truth. In the case of polynomial regression, the data was generated from the function y equals 3x squared plus x plus 2 plus epsilon, with similar noise and input distribution as before. The initial model parameter, theta_0, was also set for a regression task from real numbers to real numbers. Training showed effective convergence, with the model adapting to the polynomial nature of the data. For sinusoidal regression, the data was created from the function y equals sin x plus 2 plus 0.01 epsilon, with x ranging from -3 to 3. Fitting a sine function was challenging for neural networks, but using a more powerful model like GPT-4o resulted in better extrapolation compared to LLaMA3. By incorporating prior knowledge about the periodic nature of the data, we achieved a good approximation and improved extrapolation capabilities, especially with GPT-4o. This highlights the importance of the underlying model's capabilities in handling different types of data. Section Summary. In this section, we explore different regression tasks including linear, polynomial, and sinusoidal regression. For linear regression, we observe the model improving and converging to the ground truth by adjusting the scaling factor. In polynomial regression, we see the model evolving from a linear to a quadratic form to better capture the nonlinear relationship between inputs and outputs. Lastly, in sinusoidal regression, we find that adding a prior based on the periodic nature of the data significantly improves the model's extrapolation capabilities compared to a neural net. Section: Two blobs classification. In this section, we worked on two different classification tasks: two blobs classification and two circles classification. In the two blobs task, we created a simple linearly separable dataset with two blobs on a 2D plane. We started by initializing our model for binary classification. The optimizer analyzed the data and updated the model to have a linear decision boundary that worked well. However, the training loss did not immediately converge, so we looked deeper into the optimizer's feedback. The optimizer suggested making the model more complex to improve its performance, leading to a deep decision tree with a good margin from the data. Moving on to the two circles task, we generated a dataset with data points on two concentric circles, making it non-linearly separable. We added a prior belief that the decision boundary should be a circle. The optimizer used this information to update the model with a circular decision boundary. As training progressed, the optimizer focused on fine-tuning the radius and center of the circle. Without the prior belief, the model could still learn well but showed more variability in performance initially. We then compared our variable prompt learning (VML) approach with automatic prompt engineer (APE) on tasks like linear regression, text classification, and medical image classification. VML was able to learn more detailed and useful insights from the data compared to APE, which provided more general descriptions. In the medical image classification experiment, we demonstrated the effectiveness of VML in improving model performance over time. Models initialized with prior knowledge outperformed those without, showing the importance of encoding domain-specific information. The interpretability of VML models is crucial for applications in the medical field, allowing validation by professionals and providing grounded predictions. Section Summary. In this section, we explore the classification of two blobs on a 2D plane, where we observe the effectiveness of training and the convergence of the model. We investigate the optimization process and model updates to achieve a linear decision boundary, leading to a deep decision tree for accurate classification. Additionally, we delve into the classification of two circles, emphasizing the utilization of prior information to guide the model towards a circular decision boundary, showcasing the importance of inductive bias in improving model performance. Section. Concluding remarks and limitations. In this section, we present a new approach to machine learning called Verbalized Machine Learning, VML, and share our findings from various regression and classification case studies. Our experiments demonstrate that VML is effective in handling these common machine learning tasks, showcasing the potential of language models as function approximators. Despite its success, there are some limitations we need to address. Firstly, training in VML still faces challenges due to significant variance, partly stemming from the randomness in language model, LLM, inference and the design of the optimizer. Secondly, the numerical errors in LLM outputs lead to unavoidable fitting inaccuracies. Even if the LLM grasps the symbolic expression correctly, there can still be errors when making predictions on specific input values. This highlights the difficulty LLMs have in interpreting numbers accurately. Thirdly, the data dimensionality and batch size in VML are constrained by the context window of LLMs, restricting its ability to handle high-dimensional data or large batch sizes. Moving forward, we aim to enhance VML by incorporating insights and principles from traditional machine learning methods. We would like to acknowledge the discussion on the relationship between LLMs and computers in our blog. The concept behind the VML framework is inspired by treating LLMs as modern computers, where the verbalized model parameters serve as a way to program the LLM. We draw a parallel between VML and the von Neumann architecture, as both involve inputting data and program instructions through the text prompt in VML. WL received support from the German Research Foundation, DFG, SFB 1233, Robust Vision, Inference Principles and Neural Mechanisms, TPXX, project number 276,693,517. This work was partially funded by the Deutsche Forschungsgemeinschaft, DFG, German Research Foundation, under Germany's Excellence Strategy, EXC number 2064/1 project number 390,727,645. Additionally, this work was supported by the German Federal Ministry of Education and Research, BMBF, Tübingen AI Center, FKZ, 01IS18039A. RB acknowledges funding from the German Research Foundation, DFG, for Project 448,588,364 of the Emmy Noether program. We express our gratitude to the International Max Planck Research School for Intelligent Systems, IMPRSIS, for their support of Tim Z. Shao.